Good morning. As you can see from these previous lessons, we have already learned quite a bit about ideal parallel plate capacitors. We typically illustrate ideal parallel plate capacitors like this. Bobby, please remind us of the equation for the capacitance of an ideal parallel plate capacitor.
Okay, the capacitance of an ideal parallel plate capacitor equals kappa, the dielectric constant of the dielectric between the plates, times epsilon naught, the electric permittivity of free space, which is also called vacuum permittivity, which is a fundamental physical constant equal to 8.85 times 10 to the negative 12 Coulombs squared over the quantity newtons times meter squared. That times capital A, the surface area of one of the plates, all divided by lowercase d, the distance between the two plates.
Thank you, Bobby. Today we are going to build a real parallel plate capacitor and measure the dielectric constant of printer paper.
Flippin' physics.
Here you can see is the bottom plate of the capacitor, a thin sheet of aluminum foil. On top of that, we place a single sheet of printer paper. Printer paper is what we are going to use as our dielectric. And then on top of that, we place another sheet of aluminum foil, which will be the top plate of our homemade capacitor. Some things to notice here. First off, the sheet of paper is wider than both pieces of aluminum foil. Why do you think it has to be like that?
To make it so the two plates do not touch one another.
Oh yeah, if the two plates touched one another, then charges would easily be able to transfer from one plate to the other.
That's right. The dielectric material is an insulator which prevents charges from moving between the two plates.
Yep.
That is correct. Now, it is hard to see from this photo. However, realize the bottom plate of our capacitor ends a little bit before the edge of the paper for the same reason. That means the area of our homemade capacitor looks like this and has a length of 0.27 meters and a width of 0.205 meters. Again, that is the total area where we have both sheets of aluminum foil and the sheet of printer paper making a parallel plate capacitor. Any space outside of that rectangle does not have all three materials.
Mr. P?
Yes, Bobby?
Why did you use only two significant figures for the length when you used three significant figures for the width? I mean, you must have used the same ruler to measure both of those distances, so you should be able to also measure the length to the millimeter, right?
Okay. That is a very good question, Bobby. As we vary the number of sheets of paper between the two aluminum plates, you will see that it was a bit difficult to keep the horizontal location of the same each time. For that reason, I felt I could only measure the length to the nearest centimeter. And you will see later in the lesson that any more than 2 sig figs would probably be too accurate for this calculation of the dielectric constant of printer paper.
Okay.
Now, before we measure the capacitance of our capacitor using this digital multimeter, we're going to do our best to make sure the plates of our capacitor and our dielectric are as flat as possible and try to remove as much air between the plates as possible. We do this by adding a large dictionary on top of the capacitor, and also roughly 54 kilograms of mass, which has a weight of roughly 120 pounds here on Earth. Again, we are trying to flatten the capacitor out and remove any air between the plates. Now, I am going to take the test probes of the digital multimeter, which are red and black, and touch each one to a plate of the capacitor. And you can see we get a reading of 11.73 nanofarads. Let's start a data table with a column for number of sheets and a column for capacitance in nanofarads. Now, I take all of that mass off the capacitor, take off the top plate, and add one more sheet of printer paper, then put the top plate of the capacitor back on, and then add all of the mass back on top of the capacitor, and then measure the capacitance again. This time it reads 7.73 nanofarads, which I have added to the data table.
Mr. P,
Yes, Bo?
do you really have to add all of that weight on top of the capacitor to make this work?
Yes, Bo, I do. Let me show you why. For our next measurement with 3 sheets of paper, when we measure the capacitance with just the book on the capacitor, the capacitance measures 3.87 nanofarads. with an additional 50 pounds of weight on it, measures 5.28 nanofarads. Adding 40 pounds of weight gives a new measurement of 5.70 nanofarads. And with the full 120 pounds on there, the capacitance measurement is 5.94 nanofarads. So yes, we definitely need those 54 kilograms of mass on there.
That makes sense.
Okay.
Sure.
And we can take more measurements. Four sheets of paper result in a measurement of 5.12 nanofarads. 6 sheets of paper measures 3.74 nanofarads. 8 sheets of paper is 3.06 nanofarads. 11 is 2.34 nanofarads. And I want to pause here for a moment. Previously, I pointed out that the illustration we normally use for a parallel plate capacitor exaggerates the distance between the two plates, and that a more accurate representation looks more like 3 solid parallel lines like this. Well, you are now looking at a real parallel plate capacitor, and I hope you can see it really does look more like 3 solid parallel lines.
I see it.
Yeah.
Yep.
Good. Now, 15 sheets of paper is 1.82 nanofarads, 20 is 1.42, 30 is 0.99, 40 is 0.77, and 50 sheets of paper measures 0.63 nanofarads. Okay, on our data table, we now have number of sheets and capacitance in nanofarads. Now, our goal is to measure the dielectric constant of the printer paper. To do that, we're going to create a graph of these data where we can draw a best fit line through the data points and determine the dielectric constant using the slope of the best fit line. To do this, we need to linearize the data. This starts with the slope-intercept equation for a line. Bo, what is the slope-intercept equation for a line?
Sure. That is y equals mx plus b.
We usually use the word slope instead of lowercase m for slope in that equation.
Why?
Really? Lowercase m in physics?
Oh, sure. Math.
Or meters.
Or milli as in millimeters?
Okay. Y equals slope times x plus b, where b is the y-intercept value of the line.
Oh, and we can adjust the capacitance of a parallel plate capacitor equation to make it equal to the parenthetical quantity, the dielectric constant times electric permittivity of free space times plate surface area, all times 1 over lowercase d, the distance between the plates.
And when we compare that to the slope-intercept equation of a line, we can see that to linearize the data, we need to put capacitance on the y-axis, 1 over distance between the plates on the x-axis. The y-intercept should equal 0. And when we do that, the slope of the line represents the dielectric constant times vacuum permittivity times plate surface area.
But we do not have lowercase d, the distance between the plates, for each trial yet.
We don't?
We have number of sheets, but not distance between the plates.
All we need is the thickness of a single sheet of paper. We can multiply that by the number of sheets to get the thickness of the dielectric, which is the same as the distance between the plates.
Yep.
Yeah.
That is all correct. Thank you. As you can see, if we measure a single sheet of paper using a digital caliper, we get a value of 0.10 millimeters. If we instead take a pack of 500 sheets of paper and measure the thickness of all 500 sheets of paper, it measures to be 51.09 millimeters, or 0.05109 meters. We can get a more accurate measurement of the average thickness of a single sheet of paper by dividing 0.05109 meters by 500. That means the value for lowercase d with a subscript of 1, the distance between plates for our first trial, and the average thickness of a single sheet of paper is 0.000100218 meters. And to get the value for the distance between plates for each trial, we multiply the number of sheets by the average thickness of a single sheet of paper. And you can see I have added that to the data table. Also, as y'all figured out before, we need to add the inverse of the distance between the plates to the data table, which I have now done. From there, we are creating a graph of these data with capacitance in nanofarads on the vertical axis and the inverse of the distance between plates in units of the inverse of meters on the horizontal axis. And we can then add all the data points. And then we can add a best fit line, which best approximates all these data. And we can add the equation for that best fit line as well. Remember, the goal is to solve for the dielectric constant of the printer paper. We can use the slope of the best fit line to do this. Bo, what is the slope of this best fit line?
0.00118.
Sure, but 0.00118 what? What are the units of the slope?
Okay. Slope equals rise over run. So the units for the slope would be whatever we get when we divide the units on the vertical axis by the units on the horizontal axis.
And that is?
Nanofarads divided by 1 over meters, so nanofarad meters.
Please convert nanofarads to farads.
Well, we multiply by 1 farad over 1 billion nanofarads because there are 1 times 10 to the 9th nanofarads in 1 farad. So the slope is 1.18 times 10 to the negative 12 farad meters.
Thank you, Bo. Bobby, what units do we get for the slope if we use what we determined using the slope-intercept equation for a line?
We determined that the slope represents the dielectric constant times vacuum permittivity times plate surface area. The units for that would be, well, the dielectric constant has no units. The units of vacuum permittivity are Coulomb squared over the quantity newtons times meters squared times the units for surface area, which are meters squared. So Coulomb squared over newtons?
Well done, Bobby. Now, those two units we got for the slope should be the same, right?
Absolutely.
Yeah.
Sure.
So, Billy, are farad meters the same as Coulomb squared over newtons?
Now that is a difficult question. I do not know.
Well, let's take the time to make sure.
Certainly. Let's start by determining the units for farads. By definition, capacitance equals charge per electric potential difference. In terms of units, that is, farads equals coulombs divided by volts. Now we need the units for volts. Electric potential difference equals change in electric potential energy divided by charge. In terms of units, that is, volts equals joules divided by coulombs. Substitute that back in for farads and we get coulombs over joules per coulomb. That means farads equals coulomb squared over joules. Now let's determine the units for joules. Work equals force times displacement times the cosine of the angle between the direction of the force and the direction of the displacement, where we use the magnitudes of both force and the displacement. The units for that are joules equals newtons times meters times no units. The cosine of an angle has no units, so a joule equals a newton meter. And we can substitute those back into the units for farads. We get that farads equals coulombs squared divided by the quantity newton meters. And going back to the units for slope, we can substitute that, what we have now, for farads. Slope equals 1.18 times 10 to the negative 12 farad meters. So farad meters equals coulomb squared divided by the quantity newton meters, all times meters. Meters cancel out, and we get that farad meters equals coulomb squared divided by newtons. So yes, they both result in the same units for slope.
Yes, Billy, that is correct. Well done.
Yeah, so I am impressed by Billy. However, Mr. P, that does seem a bit excessive. I mean, we already knew they should have the same units before Billy did all of those unit gymnastics, right? So I do not really see the point in going through all of that.
Okay. You know what? It is time for a sidebar. Hi. So this message is for you. Yes, you. The student watching this video right now who agrees with Bo. You know who you are, and I know you are out there. Yes, it may feel to you to be a bit excessive to have walked through all of those units. However, know that understanding everything Billy just reviewed will help you very much in the long run. Yes, knowing and understanding units will help you better to be able to understand all of this. So no, it is not excessive. It is extremely helpful. Any questions?
No.
So that's what Bo's been looking at.
Moving on. Now that our units are all squared away, we can confidently solve for the dielectric constant of this printer paper. We know in this example, slope represents the dielectric constant times vacuum permittivity times plate surface area. Therefore, the dielectric constant equals slope divided by the quantity vacuum permittivity times plate surface area. And we know plate surface area equals length times width because it is a rectangle. So we can substitute in all our numbers to get 1.18 times 10 to the negative 12 divided by the quantity 8.85 times 10 to the negative 12 times 0.27 times 0.205, which equals 2.408913, or roughly 2.4, with no units because the dielectric constant has no units. And in a previous lesson, we showed values for the dielectric constants of various materials as published on the Engineering Toolbox website. They list the dielectric constant of paper to be between 2 and 4. And what we determined is in that range. I think we can say,
the physics works. The physics works. The physics works. The physics works, The physics works.
But does it really?
What do you mean, Billy?
You said we were going to linearize these data and, well, they do not look very linear to me.
Oh, that is a good point.
Nice. I'm glad you brought that up, Billy. That is definitely something we should talk about. I agree that these data look like they could perhaps follow a square root function, y equals the square root of x, rather than a straight line.
So the physics did not work?
Well, that is an interesting question. Remember the equation we used for the capacitance of a parallel plate capacitor?
Yeah.
Sure.
There was one important word we used to describe the type of parallel plate capacitor for which this equation is valid. What was that word?
Ideal. This equation is valid for ideal parallel plate capacitors.
And what assumption did we make about the distance between the two plates when determining this equation for the capacitance of an ideal parallel plate capacitor?
Right. We assumed that the distance between the plates was very small compared to the linear dimensions of the surface area of the plates, so small that the plates could be considered to be infinitely large.
Oh.
Right. It appears that this capacitor is not actually ideal. It appears the capacitor is less and less ideal the larger the distance between the two plates is, or the smaller the value of the inverse of that distance. In an ideal parallel plate capacitor, the electric field is assumed to be perfectly uniform and confined entirely between the plates. That is how we showed it in the first illustration. In reality, the fringe electric fields extend beyond the edges of the plates and look more like this. When the plates are close together, in other words, lowercase d is very small and the inverse of d is very large, the contribution of the fringe electric field is very small compared to the strong, concentrated electric field between the two plates. So the capacitor is nearly ideal. However, as the dielectric gets thicker and the distance between the two plates increases, the fringe electric fields become proportionally more significant. The fringe electric fields increase the capacitance beyond what the ideal parallel plate capacitor equation predicts. These added fringe electric field lines exist because the capacitor can now store additional charge, more than the ideal equation accounts for. If we rearrange the ideal parallel plate capacitor equation, we get that the dielectric constant equals the ideal parallel plate capacitance times distance between the plates, all divided by the quantity vacuum permittivity times plate surface area. We can use that to calculate an observed dielectric constant for each data point. For the first data point, we get a dielectric constant of roughly 2.4. And you can see I have added all the rest of the dielectric constant calculations to the data table. And you can see that for larger distance between the two plates, because the measured capacitance is higher than its hypothetical ideal value due to the fringe electric field effects, the calculated dielectric constant is increased. This is because the ideal parallel plate capacitance is in the numerator of the equation. In fact, you can see that the larger the distance between the two plates, the larger the effects of the fringe electric field, the larger the observed dielectric constant, and the less accurate the observed value of the dielectric constant becomes. In summary, the apparent increase in the dielectric constant with distance between the plates is an artifact of fringe electric field effects growing more significant relative to the ideal field as plate separation increases. The capacitor becomes less ideal with larger distance between the plates, and the excess capacitance inflates the observed dielectric constant.
And each sheet of aluminum foil actually extends farther on one end of the capacitor than the paper. That probably increases the electric field too. Why did you do that?
He did that because he needed to be able to touch the multimeter test probes to the capacitor.
Yeah, that makes sense.
But the graph also showed that the Y-intercept of the best fit line was positive. According to our linearization formula, the Y-intercept should have been 0, right, Mr. P?
Oh, yeah. That could be caused by the internal capacitance of the multimeter.
Yeah, the test probes, leads, and multimeter do contribute a small baseline capacitance to every reading. However, because the multimeter clearly shows a capacitance of nearly 0 when not connected to the capacitor, that baseline must be very close to 0. Actually, the baseline appears to be somewhere between 0 and 0.01 nanofarads because the multimeter oscillates between 0 and 0.01 nanofarads when it is not connected to anything. And going back to the Y-intercept of the graph for a moment, the fact that the Y-intercept is not equal to 0 indicates that our equations are not quite valid. Yes, the physics works. However, in this case, the physics working is that it tells us that while our calculations are approximately correct, the more printer paper we add between the two pieces of aluminum foil, the less accurate our data is. And we should probably limit our calculations to very small numbers of sheets of paper and, if possible, try to find thinner paper. Thank you very much for learning with me today. I enjoyed learning with you.